Hi folks, this is one of my all-time favorite torque problems, mostly because I think most of us want to find information about our bodies, and this simple technique can be used to find the center of gravity of your body. When I teach face-to-face lab classes, I always do this with my students, and it's always a fun day. Here's how this works. I have a long board, and this board is a good heavy stout board. It has a weight of 30 pounds, and so its downward force vector in the middle of the board is going to be 30 pounds. That's actually where its center of gravity is located. Now I put this board on 2 bathroom scales. Now, if you're going to try this at home, and you probably do not have a couple bathroom scales and a big board lying around, but if you get a chance, this is kind of fun. I put it on 2 bathroom scales. The Y2, I want the board level, and of course I don't want to be on the top of the glass of the scale. The person whose CG we're going to measure is going to actually lay down on the board, their head next to one end, and then they're just going to lay on the board. I want to know where their center of gravity is. So they're going to have somewhere in the middle of their body, they are going to have a force of gravity down on, let's call it FP for the person. Well, this is a torque problem, and this is a system that is not supposed to rotate at all. So what do I do with it? Well, what I do with it is I'm going to put an axis of rotation somewhere. And I know in this problem that the foot end of the scale reads 80 pounds. Now what that means is the board is pushing down on the scale with 80 pounds, but that also means the normal force upward provided by the scale is 80 pounds. So what I'm going to do is I am going to pretend this is a rotational system. I am going to put my axis of rotation right underneath the head of the person. And I am going to say that there are torques making it rotate in the clockwise direction. The weight of the person and the weight of the board are all going to make the whole system rotate in that direction. And the normal force caused by the scale down here is going to make the whole system rotate in a counterclockwise system. Well, this is a very stable situation. So stable that I know the sum of the torques on it equal 0. So my clockwise torques are going to equal my counterclockwise torques, or my negative torques are going to be equal to my positive torques. And for each one of these weights and lever arms, I am going to write a force lever arm equation. So let's go through and get some numbers for the actual distances. The board itself is 2 meters long, so I know this normal force down here is directed 2 meters from my pivot. The weight of the board is going to be in the geometric center of the board. If the board is 2 meters long, what's the lever arm to the center? So the lever arm here is going to be 1 meter. And what I want to know is I want to know the lever arm of the person. I want to know how far from the top of this person's head to their CG. And it's going to be sort of in the middle-ish part of their body. So let's go ahead and do this. So I'm going to start with the force of the person is a downward negative torque times the lever arm of the person, which I do not know. The other torque making the whole system rotate in this clockwise direction is going to be the force of the board itself, the weight of the board, times the lever arm of the board, that's that weight. And that's going to be equal to the normal force of the scale pushing upward and the lever arm down to that normal force. Now let's put some numbers in. The force of the person is going to be the weight of the person, and I was told in the problem that this fellow weighs 170 pounds. I don't know where his CG is. That's what I'm after. The board itself weighs 30 pounds, and actually in my lab I actually have a 30-pound board, so that's why I use 30 pounds. The lever arm of the board is 1 meter. The normal force on the other end is 80 pounds, and the lever arm to the far end is 2 meters. Well, this is going to be 160 pound meters. This is going to be 30 pound meters, and this is going to be 170 pounds times the lever arm of the person. Now, I talked about this in the last problem. You can play a little bit fast and loose when you're summing torques. If that is all you're doing, you can play a little fast and loose with units. If you are relating this to anything else, then you have to be not so naughty, but as long as all your distance units are the same, all your force units are the same, if you're just summing torques, you can be a little naughty with the units. Isn't that wild? I know. All right, I'm going to subtract 30 pound-meters from both sides. These are going to cancel, so 70 pounds times the lever arm of the person will be equal to 60 minus 30, 130 pound-meters. Divide both sides by 170 pounds, and pounds will cancel, and what I'm going to end up with is the lever arm of the person is going to be 0.675 meters. Now, what does that mean? That we measured our pivot at the top of this person's head. That's where we placed our pivot. So what that means is if I stand this person up and I measure from the top of their head down 0.76 meters, that's going to be their CG. So it's a lot of fun to do, and we'll see you next time. Bye-bye.